In the previous section, we described various considerations when compiling an FPGA VI. By the end of this module, you will be able to describe basic optimizations you should implement as basic programming practices for all FPGA VIs. So in this section, we're going to talk about basic optimizations that you'll want to make on all FPGA VIs, and these are just kind of best practices that you should do. So the ones that we're going to describe are relatively easy to implement. They shouldn't require any major changes in your code architecture. They should be basic programming practice for all FPGA VIs. And these optimizations that we're talking about in this particular section primarily affect FPGA size. So these optimizations will help your FPGA VI use less FPGA resources. So here we see the types of basic optimizations that we're about to talk about. So we'll talk about limiting front panel objects on the top level VI, how to use small data types, and how to avoid some large functions. Okay, so let's talk about limiting front panel objects on a top level VI. So each front panel object on your top level VI must have logic to interact with your host VI. So every control, every indicator is going to consume a decent amount of FPGA resources because it's going to have to implement logic on the FPGA to be able to send that information from the FPGA to your host. So the less front panel objects that you have, the more resources you'll save. So in general, only put controls and indicators on your front panel, on your top level front panel, and limit to only the ones you need. Each read and write from the host to the FPGA is broken down into 32-bit packets to transfer across the bus. If you have something that's greater than 32 bits, then it'll have to be broken down into 32-bit packets and transfer those across the bus. So consequently, arrays and clusters with more than 32 bits are going to require an extra copy on the FPGA to guarantee all the data is read or written coherently. Another optimization that you'll want to do is you want to limit front panel arrays. So in general, you should avoid using arrays on the front panel, but if you have to, you need to make sure that all arrays are a fixed size. And the way that you do that is you can right-click an array and then go to Set Size, and then that'll allow you to make that array a fixed size. So a compilation is going to fail if the array size is larger than the available FPGA resources. Arrays can quickly use large amounts of FPGA resources, and the reason for that is because each bit in the array uses its own flip-flop on the FPGA. So if you think about it, if you've got this huge array on your front panel, you can quickly use up all the FPGA resources because all that data is going to use up a bunch of flip-flops on that FPGA. And this is one of the number one things that's going to take up a lot of space on your FPGA. So one of the best optimizations that you can do is if you look at your code and you've got huge arrays that contain lots of data on your front panel, you want to get rid of those. One way that you can get rid of those is you can replace them with FIFOs or memory items. And that's something that we'll talk about a bit more in the lesson on sharing data on FPGA. So just remember that for now. The key thing is huge arrays on your front panel are going to eat up all the space on your FPGA. So let's talk about bit packing Boolean logic. So each control, like we said before, is going to have overhead in addition to the size of the data type. Okay, so each control you have there is going to take up some space on your FPGA resource because it's going to have to implement FPGA resources to handle the communication between the FPGA and the host. So if we look at this example here, we've got 8 Booleans, and for each Boolean that you see there, it's going to have to implement a resource to communicate that data between the FPGA and the host. So one way we can save some space is we can use fewer controls, but communicate that same information. So if you look on the right, what we've done is instead of using 8 separate Boolean controls, we're just going to use an 8-bit unsigned integer to represent those Booleans. So for example, if you have the number 255, that's going to represent 1111, 1111 in Boolean. So because we only have one control there, it's going to use up less resources on our FPGA, but we can actually indicate the same information with that data type, right? So if you take that numeric, use the function to convert the number to a Boolean array, and we index that array, we can get that same Boolean information out programmatically. But this way we save space on the FPGA. So in general, if you want to save space on your FPGA, what you can do is use the smallest data type that you need to implement your functionality. So let's take a look at this example here. So if you look on the left, we've got a case structure, and if we look at the data type for that, it is a unsigned 32-bit integer. Well, if you think about it, you probably don't have 2 to the 32 cases in your case structure, right? You probably have like 10 to 20 and something like that. So if we look on the right, we've optimized that and we're using an unsigned 8-bit integer. So now our case structure is only handling the numbers from 0 to 255. So chances are you have less than 255 cases in your case structure. So in this case, we're saving some space because we're using a smaller data type. A U8 is going to be something smaller than a 32-bit number, right? So on this slide, we're going to talk about coercion. If we look at that top example, we've got some code that's generating U32 data, and then we're sending that data to a I16 indicator, and we see that we have a red coercion dot, okay? If you see any coercion dots, what's happening is the compiler must determine the proper data type, and it can lead to inefficient data conversion. So instead of leaving it to chance, it's better to specify that actual conversion. So if we look at the bottom, what we're doing instead is we're taking that code that's generating U32 data, we're explicitly using a function to convert that data type into an I16 data type, and then sending it to the indicator. And notice at the bottom, we don't have any coercion dots. So in general, if you want to make sure everything is going to be optimized, try not to use any coercion dots and implement that coercion yourself using functions. And that will generally lead to more efficient implementations. So now we're going to talk about avoiding large functions. So on the FPGA, not all functions are equal, meaning not all functions are going to take up the same amount of space. So for example, we can take a look at these two block diagrams, and they're both trying to do the same thing. They're both trying to divide by 4. So let's take a look at the quotient remainder function. So if we use this on a FPGA, we're taking x and we're putting into this function, dividing by 4, and getting the quotient. So on the right, we're doing the same thing, but we're using a scale by power of 2. So if you're taking x and you're scaling it by the power of 2 to the negative 2, mathematically that's the same thing as dividing by 4, and we get our quotient. So functionally they're the same, but in terms of how many resources it takes on the FPGA, it's going to be vastly different. So if you look at the quotient remainder function, this is a very large function. This is going to take up a lot of resources on your FPGA because the way that it's implemented, it's going to have to figure out the quotient and remainder for a variety of things, and it's going to take up a lot of space. So if you look at the scale by power of 2, in the FPGA world, when you're scaling by a power of 2, it's a simple bit shift. It's not going to take any resources on the FPGA to actually implement that. So dividing by 4, it's a lot more efficient to use the scale by power of 2 function instead. So on this slide, we're talking about the quotient and remainder function. So again, the quotient and remainder function is going to take up a lot of resources. For each operation, it's going to have to implement resources to figure out what the quotient is and what the remainder is. So there's additional resources consumed for that, even if all you're looking for is the quotient. So if we look at these two block diagrams, one common place where people would use a quotient and remainder function when they don't need to is they're trying to implement some sort of counter on their loop. So if you look at that top one, what the user is trying to do is they're just trying to make the output of that quotient and remainder go from 0 to 9. So it's just going to go 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, and then go back to 0, 1, 2, 3, 4, 5, 6, 7, 8, 9. Okay? So this implementation, because it uses the quotient and remainder function, is going to take up a lot of space on the FPGA. One way you can save some of that space is you can implement it without using the quotient and remainder function. So if we look at our bottom block diagram, instead we're using a shift register and we're initializing it with 0, and then we're going to compare that with a greater than function to 9, and then we're going to output that to a select function. So essentially what's going to happen is the first iteration, it's going to output a 0. It's going to add a 1 to it. So the next iteration, the select function is going to output 1. And the next iteration, it's going to output 2, 3, 4, 5, 6, 7, 8, 9. And then once that number gets greater than 9, this functionality that we've implemented is going to reset it back to 0. So the select function will output 0, 1, 2, 3, 4, 5, 6, 7, 8, 9. And then it's going to go back to 0, 1, 2, 3, 4, 5, 6, 7, 8, 9. So the bottom implementation, we're using different functions to implement that same functionality. However, it's going to be taking up a lot less resources on the FPGA. In this slide, we're going to talk about the scale by power of 2 function. if we were using a scale by power of 2 function and the input for power is a control, then it's going to take up a lot of resources on our FPGA. The reason for that is if the input for power is a control, then it's going to have to implement logic on your on the FPGA hardware for all powers, all possible powers coming from that control. However, if you wire a constant to that input, to the power input, the function consumes no space on the FPGA because all the FPGA is doing is a simple bit shift. So the scale by power of 2 is a very useful function if you ever need to divide by a power of 2. So for example, if we look on the left, we're using the quotient and remainder function, and it's trying to divide something by 4, but because it's using the quotient and remainder function, it's going to take up a lot of resources on the FPGA. Now we can change that and make it a lot more efficient by using the scale by power of 2. So we're just scaling it by a constant of -2, which is mathematically dividing it by 4 to get our quotient. And that's going to consume no space on the FPGA because it's a simple bit shift. So in general, we see that when you're writing some logic, when you have to implement it on hardware in the FPGA, there's some extra considerations that you have to make, because if it's being implemented in hardware, the consequences of that function could possibly take up a lot of space, or it could take up less space.